The last few videos have described Heisenberg's uncertainty principle, which relates uncertainties in x, position, and momentum p, and how we can use this relation to estimate, say, the energies of an electron in an atom. Now, in this video, I'm going to talk about a similar relation that relates time and energy. So the uncertainty relation relates position and momentum. That the product of the uncertainty of these two uncertainties is about equal to the Planck's constant. So this refers to, say, an electron along, say, a certain axis x with a certain momentum p. Okay. Now there is a corresponding relation which relates time. Which relates time and energy. So it says that the uncertainty in the time and the uncertainty in energy, when you multiply them together, is of the order of the Planck's constant as well. What does this actually refer to? Okay. Now this can refer to actually say the wave of light, for example. If let's say I have let's say this is a wave of light of a certain frequency f, then we know that hf is the energy of the photon of this light. Now suppose that this wave, as I've described previously, if we talk about a wave of a particular wavelength or frequency, it must mean that it must imply that we're talking about a wave that is infinitely long, right? Because if it has a definite wavelength, it just means that it must keep repeating itself with that wavelength. So that's the idea of a wave of a particular wavelength or frequency. But what if this wave does not last forever? So this time, let me think of this as a graph in, say, the time axis rather than the x-axis. So let's imagine that there's this wave, this electromagnetic wave or light wave that oscillates for a period of time delta t. It only oscillates for a period of time delta t and then stops. It's like you switch on the light for, say, 2 seconds and then you switch it off, for example. But if you're switching on a lamp for 2 seconds, that's probably not the right place to apply the uncertainty principle, because the time scale might be too long and the lamp would be emitting lots of photons at random. So we'll look at a more specific example in a moment. But let's say we have a light wave that lasts for a short time, delta t. So if it only lasts for a short time, then this relation would tell us that the actual energy of the light, would have a range of energies. It would not be a definite energy anymore. Because this definite energy E equals to hf, it is only true if we have an infinitely long wave. Then we have a definite F and therefore a definite E for the photons in this light. But if we have a finite length, right, not infinite, just finite, some fixed time, then it is no longer a definite frequency. Right? Strictly speaking, it's no longer a definite frequency anymore. And when we have just a finite time, then this uncertainty relation would tell us that actually there would be a range of energies in here, meaning a range of different frequencies or wavelengths, or rather because there is a range of different wavelengths. Now in the previous video, we have already seen how a short pulse of wave, right? How a wave with a short extent of delta x, how it could be made up by adding a number of different wavelengths together. So in the same way, we can imagine making this up by using a number of different frequencies. So I'll just illustrate this with similar graphs as before. So imagine that I start with a number of different wavelengths. Say that's one wavelength. That's maybe a longer wavelength. And a shorter wavelength perhaps. I should say period. I want to talk about period this time. So it's in the time axis. Okay, so if I add this up, I would end up with a situation like I had for the original X and P relation, the last video. I will get constructive interference where the peaks meet around here, or at a place where they meet. So I get a bigger peak, and the other peaks, because they start getting out of phase, right, because the peak and trough might come together, the amplitude might start going down and getting a bit random. Okay, so the idea is that by adding, this time I will talk about period instead of wavelength, right? That one cycle in the time axis is called one period. So by adding different periods together, and different periods means different frequencies, of course, frequency is 1 over the period. So by adding the different frequencies together, I would end up with a wave that lasts for a finite time, rather than a wave that lasts forever. Okay, that goes on forever in the time axis. I would end up with a wave that mostly is non-zero over a range of time, but beyond that it could get quite small or become zero because they interfere a lot randomly, and you don't get much amplitude away from this pulse. So you see that this picture as I've drawn it is very similar to the one I drew for X and P in the last video, or in 2 videos ago. Okay, so in that sense, in a similar sense, when we would know that if a wave lasts only for a certain range of time delta t, there must be a corresponding range of frequencies, right? Or it must be made up of a corresponding range of frequencies, and therefore of energies. So therefore, like in the case for the x and p, there can be a relation that relates the range of t to the range of energy E. And it is actually, and just to see in the next few steps, I'm just going to give an idea of why this uncertainty relation for E and T looks so similar to the one for X and P. So here's how it works. Remember that P, okay, remember what P and X are. They refer to, for X and P, they refer to the x-axis, where we have a wave of a certain wavelength, okay, and if you remember that P is equal to h over lambda. That's the de Broglie's relation. Okay. Now, and in the case of let's see, in the case of time and energy, when we talk about frequency and period, what we have is we have this wave in the time axis. We have the t here. So frequency is 1 over t. Now we know that E is equal to h over f. Now if you substitute this into here, you will find that for this case, when we are talking about, say, the photon, and we are talking in the time axis, we have E is equal to hf, but hf is, f is 1 over t, right? So this is the hf, right? This is hf, but f is 1 over t. Now if you compare these two, right, you can see that it's as if P correspond to E and lambda correspond to the T, right? The lambda is the repeating distance, okay, and the period, the big T, is the repeating time. It's repeating time, that's the repeating distance. So the lambda here corresponds to x, right? It's a distance in x, and the t here, the period here, is a distance in time. Okay, so what we have is that we have a similar relation between momentum and distance, meaning the relation between energy and time is similar to the relation between position and distance. In fact, they are exactly the same. I just replace P by E and the lambda distance by the period time, and you get this equation. So which is why all you need, because of this similarity and because they're both about waves, that's why you can just take Heisenberg's uncertainty relation and just replace the x by t, P by E, and you would automatically get the correct relation, uncertainty relation, for time and energy.